Welcome to this intro video for Module 3 of MCET.450 Advanced Mechanics. In this video, we will review stress elements. The stress element represents a specific location on a machine member or body. Much like finite element analysis, we are looking at a specific element on our component at a location of interest. We generally use a cubic element as this facilitates easiest analysis in terms of a 3D coordinate system. Stresses that are normal to or perpendicular to the faces of the elements are considered normal stresses. These include stresses such as direct axial stress and bending stress. Stresses that act parallel to the faces of the cube are considered shear stresses. Transverse shear and torsional shear stresses are among these. The point at which we choose to take our element is critical, and we'll talk about that in a bit. A stress that results in the elongation of the machine member is a tensile stress and is represented on the stress element as an arrow pulling away from the face. A stress that results in compression of the machine member is a compressive stress and is represented on the stress element as an arrow going into the face. Note that the same applied load may result in both tensile and compressive stresses on the machine member. So depending on the location for the element under your consideration, you may have either compressive or tensile stress. Stresses that slide along the cross-section of the machine member are said to be shear stresses. These act on a plane defined by our coordinate system. So this will be either stress in the XY, XZ, or YZ plane. In real-world objects, the stress exists in 3D space. However, this can often be reduced to 2D spatial loading. There are three applications of stresses to a given element. The first is the actual applied stresses. This could be a bending stress, a shear stress, a direct stress, or a torsional stress. As we create our stress element, these stresses are applied and sometimes combined to be axial or planar stresses. Thus, we end up with normal stress in the X, Y, and/or Z axes, as well as shear stress in the XY, XZ, and/or YZ planes. Once we have these axial and planar stresses, we need to combine them into the principal stresses on the element. There are three principal stresses. Sometimes these are labeled A, B, and C, as shown here. Other times they are labeled 1, 2, and 3, which I believe is more common. In 2D stress, one of these stresses is always 0. In 3D stress, all three principal stresses may have some magnitude. This is an example of a Fundamentals of Engineering exam problem dealing with principal stress. It gives us a stress element and shows us the axial and planar stresses determined. There are two axial stresses. One is a 50 megapascal tensile stress in the x-axis, and another is a 10 megapascal compressive stress in the y-axis. There is also a 40 megapascal planar stress in the XY plane. From these, we are to use the formula given to find the principal stresses. Note that because it is 2D, we will have two stresses. One will be the value plus that given under the radical. The other will be the value minus that given under the radical. Tensile stresses are positive, while compressive stresses are negative. Thus, notice as the calculation is made, care must be taken to preserve the correct signs for the different stresses. This slide demonstrates the need to define a point of interest from which to create our stress element. Based on FEA, we can see that the highest stress occurs in the corner where the smaller hub meets the larger hub. That is where we should create our stress element. This slide provides a recap with graphics for the four main types of applied stresses. Remember, the process is as follows. First, define the applied stresses. Then, combine the applied stresses as axial and planar stresses on the stress element. Finally, use the information from the stress element to find the principal stresses. Here we define the concept of normal stress due to a load applied to a cross-section. Hooke's law relates the applied normal stress to the strain, deformation, and elastic modulus of a machine member under load. Note that stress is defined as force over area. Strain is defined as the change in length over the original length, and elastic modulus, also known as Young's modulus, is defined as stress over strain. By algebraic rearrangement, we find that change in length is equal to the strain times the original length. Change in length is also equal to the stress over the modulus times the original length. And finally, change in length is equal to the force times the original length divided by the modulus times the area. We'll stop the video here. In class, we will practice making application of Hooke's law. Thank you for watching.